Sure. So okay, let me just start from this slide today. So if someone has asked you to tell the number of vibrational frequencies of water, it's a fairly simple job. You know that there is a symmetric stretch, there is an asymmetric stretch, and there is a bending vibration. Okay, so it's these three, modes characterize water. But I think this is a fundamental, simple three-atom molecule. So you can easily tell these are the three vibrations. As the molecules get more and more complex in terms of the number of atoms and the number of coordination numbers around an atom, predicting the vibrational modes pictorially becomes a big issue. Because if you can associate the symmetries of these vibrations, then it's easy. So essentially, group theory gives a lot of information to physics and chemistry, like the shape of orbitals, molecular orbital energy levels or diagram, vibrational modes, rotational modes. So you can glean a lot of information on group theory. So in this course, we essentially focus ourselves into how to get information on vibrational frequencies or the symmetries of the vibrational frequencies of complex molecules. So you cannot do the complex molecules straight away. So I thought I will start with the water. That's what I did in the last class. So the three vibrations, what I talked about, are shown here from a textbook. I've just taken this. You have a A1 symmetry, that means everything is symmetric. Okay. And then there is a A1 symmetric bending in the right hand. So the atoms, kind of rock back and forth. So these angles keep changing. That's the bending vibration. Other one is an asymmetric vibration. One gets lengthened and one gets shortened. So this is the fundamental vibrations of water. Okay. And I showed in the last class that as the complexity of the molecule increases, the number of vibrations keep increasing. Okay. Then the problem becomes tougher and tougher. Okay. However, all these molecules can be assigned to one or other point group, and hence their vibrational modes can be easily deduced in terms of the symmetry symbols rather. Okay, the A1, A2 I talked about. So I also showed you the examples of WCO6 and platinum tetracyanide, where the problem gets really larger, so you cannot really solve the problem. So this is where I think I just hold on a minute. Let's get some water. So let me just quickly go through this, the set of slides what I showed yesterday. So what you see in the right top hand side is the character table of C2V point group. The C2V point group, as you know, has got an identity element. That means you do nothing, and a two-fold symmetry, which you can rotate around the oxygen. Through the oxygen, the two-fold axis rotates 180 degrees. You rotate. This hydrogen goes to this position, and that comes back here. And sigma Z and sigma xz and yz are the two planes. One is perpendicular, other one is parallel. Okay, so I also talked about what are these A's and B's and T's are all about. I'm not going to repeat all of the things, but I'm going to redo this, deducing the reducible representations, because this is, I think, is the actual application of group theory to IR spectroscopy. Now, take this molecule which is in the right hand side. So my X, Y, Z axis are, what do I do? X, Y, Z axis are now defined. I talked about in the last class about how one can get the reducible representation, which form the basis for getting the vibrational modes. So the nonlinear water molecule has got 3n - 6 vibrations, So the 3 atoms are 9 modes totally. 6 is the rotation and translational. So you get 3 vibrational modes. You can deduce all the 9 modes of, degrees of freedom, all the 9 degrees of freedom, by taking the Cartesian coordinates of each of these atoms and operating, upon this E, C2, sigma V and sigma V prime, and get these numbers, what is shown as question marks in the slide. Okay. So, and then we can also do other ways of getting this information, a shortcut, which I am going to actually talk about in this class. Let me just, before that, let me once again repeat what I told about Cartesian coordinates. How do we get this? The next slide, I have shown this molecule one more time. And the X, Y, Z axes are now actually defined here. And my symmetry elements are E, C2, sigma V, and sigma V prime. So what I'm going to do is that I'm going to operate these 9 Cartesian coordinates, okay, by the 4 symmetry elements. So when I operate the symmetry elements on these 9 coordinates, if the atom, if the coordinate remains, unchanged, I give us, value of 1. These are nothing but actually the, the traces of the matrices which represent this, symmetry operations. I will come to this a little later. I'm not going to confuse you right now with this. But the one is essentially the symmetry, trace which is coming from the matrix. Okay, so 1 if it's unchanged, -1 if it change, and if the atom itself is moved, you put 0. I think that's the easiest way of doing this. But by the middle of this class, I will say that this method is not necessary for us, but I think you need to know before you discard it. Okay, so if I operate the identity operation on these 9 coordinates, 3 per atom, 1, 3 into 3, 9, none of them get changed. So I get essentially under the tau red value of 9 for E. If I do this for C2, the 2 hydrogen atoms move their positions and then they contribute nothing. And when I rotate about Z axis, the X becomes -X and Y becomes -Y. So essentially it's -2 plus 1. So it's essentially -2 plus 1. So the value is -1. But when I do the mirror, XZ mirror is the plane of the, the board or the sheet. So all the 3 atoms are in the XZ plane. So if I reflect upon, this plane, the whole molecule, no atom actually moves, and the XZ coordinates of all the 3 atoms remain the same. So 3 into 6 remains same, and 1, that is the y-axis, becomes -y. So that becomes -3. So 6 minus 3 is 3. So to sum this up, what I have, no, one more is it. Okay, that's the other plane is the plane which is in the YZ plane. The YZ plane is perpendicular. So the HA and HB move their positions, so they don't contribute. So for the oxygen, okay, the Y and Z are plus and X becomes -X. So +2 -1, that is equal to +1. So if you go back to the slide, you have 9 here, -1 here, +3 here, and +1 here. That is the total reducible representation for this particular point group. This is the most fundamental molecule one can actually solve very easily. So you can easily operate upon the Cartesian coordinates and get this value of -9, 9 -1, 3, and +1. Now, I also told you in the last class that you can use the so-called great orthogonality theorem, which is nothing but, I just show in the next slide as a actual substitution and calculation. So your tau r is shown here. Okay, your tau r is shown here, and these are your characters, and these are your coefficients of the the symmetry operations. Okay, in this case we have no problem. Everything is 1, 1, 1. So what all you need to do is that you have to sum over the product of the reducible representation times the irreducible representation times the coefficient of the the symmetry operation. So 9 into 1 into 1, minus 1 into 1 into 1, 3 into 1 into 1, and then 1 into 1 into 1. So this is 9, this is minus 1, this is plus 3, this is plus 1. So plus 1 and minus 1 cancel, 9 plus 3, 12. 12 by 4 is 3. So number of times the A1 occurs, in other words, that total degrees of freedom which have a A1 symmetry are 3. You can repeat this exercise for other, Mulliken symbols, namely A2, B1, B2. So you can see this is 9, this is minus 1, this is minus 3, and this is minus 1. 9 minus 5 is 4, 4 by 4 is 1. So A2 occurs only once. There's only 1 degree of freedom which has a A2 symmetry. B1, 9 into 1 into 1, 9. Minus 4 times minus 1 times 1 is plus 1. 3 into 1 into 1 is 3. 1 into minus 1 into 1 is minus 1. So 9 plus 3, 12. Okay, 1 minus 1 is 0. So 12 by 4 is 3. So again, B1 symmetry occurs 3 times. B2 symmetry will be 9 minus 9 plus 1 minus 3 minus 1. That is 10 minus, of what I'm doing, plus 1. Okay, and 11 minus 3 is 8. 8 by 4 is 2. So the 12 degrees of freedom are 2 plus 2 plus 3, 5. Not 12, 9 degrees of freedom. Triatomic molecule, 3 into 3 is 9. So 2 plus 3 is 5, plus 1 is 6, plus 3 is 9. So we have found out through this exercise all the 9 degrees of freedom, what symmetries they have. So this is the advantage of operating upon the Cartesian coordinates rather than anything else as the basis. So Cartesian coordinates gives you the complete degrees of freedom in terms of the symmetries or the Mulliken symbols. So what you see here as the 3A1, A2, B1, 3 times B1 and B2. Okay. Now, taking help from this part of the period, the character table, you can essentially subtract what belong to rotation, what belong to rotation and translation. Okay, so you can see here R denotes rotation, Rx, Ry, Rz correspond to A2, B1 and B2. So I can subtract from the total degrees of freedom what I derived in the previous slide, 1 A2, 1 B1, 1 B2. I can also subtract 1 Z, 1 A1, 1 B1 and 1 B2, which all correspond to translation. In some textbooks, they will be written as a TX, TY, TZ. The one what I picked up is XYZ. Normally, if there is no prefix, it's actually translation. Rotation is always denoted by R. Okay, so I subtract minus A2, minus B1, B2 for rotation, minus A1, minus B1, minus B2 for translation. So 3A1 minus 1 minus A1 is 2A1, 0, B1, 0. So I can easily arrive to the conclusion that the symmetries of my vibrations are 2A1 and B1. The process, we also know what is the symmetries of the other two, degrees of freedom, namely rotation and translation. The next slide, I have just again shown you once again. The 2A1 is one is here, other one is here, and the B1 is here. The job is so simple for water. Okay, so if you are a science graduate without any exposure to group theory mathematics, all that you know is that there are 3 Cartesian coordinates or any if any atom has to be given an address in the three-dimensional space, you need the values of x and y and z. But you operate this on the symmetry operations, the x, y, z can change its position. For E, it is the x, y, z remains as x, y, z. For rotation, 2 of the 3 coordinates will become minus. One will remain the same. So it's minus 2 plus 1. So it will be minus 1 per atom, per unmoved atom rather. Mirror is always along the 2 axis. x and y or x and z or y and z, depending on which is a plane. Two of the axes do not change their sign, and one changes its sign. So it's plus 2 minus 1 is 1 per atom, which is per unmoved atom. That's all you have to know. Okay. For inversion, which I have not talked about so far, when you have inversion, x, y, z becomes minus x, minus y, minus z. Okay. So minus 3 will be the contributing per unmoved atom. Okay. So 3 for E, minus 1 for Cn, plus 1 for sigma, minus 3 for I. I think you should remember this will be the contribution to the Cartesian coordinates per unmoved atom when you operate upon these symmetry operations. Can I just pause for a minute and ask you whether you're able to follow what I've been telling?
Yeah, yes, Professor.
If this part is clear for all of you, then I don't have to repeat it in tomorrow's tutorial. I will do more examples rather than going through these basics. Okay, so now move on. Yes, this is the next question which I have to ask immediately myself and all of you is that are all these molecules this simple? Okay, I presume that I think you agree with me that water is very easy to get the vibrational modes. The moment you go from OH2 to NS3, life becomes somewhat difficult. It's not too difficult, somewhat difficult. This is because the rotations which involve 0, 90, 180, and 360 are easy. Okay, when you rotate through 90, about z-axis, x and y change its position. When you rotate through 180, x and y change its position and get negative, and 360 is E, nothing happens. But what about the cases where you have 120-degree rotation? This is the tricky. You have x, y, z, and you are rotating by 120 degrees. Job becomes difficult. So before I really dwell upon this too much, let me just show you the character table of C2V, C3V. C3V is a little different from what you saw in the last example, namely water. It has got actually 5 plus 1, 6 symmetry elements. 6 symmetry elements are E, C3, C32, then sigma V of sigma V prime, sigma V double prime. So the C3 and C32 primes are very easy to know what it is. So I have an ammonia molecule. I have drawn it in a slightly different way here, but for understanding, let me draw it. I'm looking up from nitrogen. I'm looking up from nitrogen, not from sideways. So these are 120 degrees angle. Okay, don't confuse this with the 109 or with the lone pair nitrogen hydrogen angles. Okay, I'm just looking from the top and I'm making a two-dimensional projection of the three-dimensional molecule. So when I do a C3 about the n axis, the axis that is running through the n, so I will be rotating by 120 degrees. So when you operate upon a symmetry element, problem occurs. Okay, when you operate upon, problem occurs for C3, while E and sigma V are okay. Okay, so when I do a sigma V, it is here. This is sigma V, and this is sigma V. That's a plane. Life is not so very difficult. Same is about the identity operation E. Nothing happens. When you rotate by 120 degrees, what I showed in the last slide, this Cartesian coordinates, this becomes an issue. You cannot say that it's -1 per unmoved atom. Okay, this could be different because it is now you have to just algebra is not enough. Now you need trigonometry. Okay, you need to know the angle of rotation and its cosine value. Okay, so Cartesian coordinates are okay for molecules like water, which is having only C2 axis, or molecules is like a square planar, PTCl42 minus. Okay, so this has got a C4 axis running through PT from the top, and then two-fold axis running this way. These are all two-fold axis. So when you have a two-fold axis 180 degrees, when you have four-fold axis 90 degrees, so life is not a big problem. But when you have this 120 degrees, or when we move on and see examples like this, what is the rotation here? 360 by 5. 72 degrees. So these rotations are going to generate x, y, z values cannot be simply a matrix transformation without using trigonometry. Okay, so you don't have to worry about it, because although the mathematicians have done a detailed derivation, subsequently people have simplified it for people who do not have a mathematical background, who still get the same answer. That's what I'm going to show in the next slide. The rotation by 0, 90, 180 are easy, others are not. How do we come? This is what exactly I've shown here. Okay, so when you have water molecule, there's x, y, z. I do 180 degrees. So okay, for a change atom, it becomes minus x minus y. I think one should be plus. That is z should be plus. Z does not change. Okay, so I'm rotating about this axis. Z does not change. But you do in ammonia, this comes here, this goes here, and this goes here. By this 120 rotation, all of them change their values, which cannot be simply denoted by minus. Okay, so how do we do this? I still want to get all my degrees of freedom, rotational, vibrational, and translational degrees of freedom, without going through this exercise of putting 4 into 3 12 Cartesian coordinates and doing symmetry operations, because anyway I'll get stuck at assigning values for the C3 axis. Okay. Before that, I'm going to tell you why there is a C3 and there is a C3-2, and why there is no C3-3. Okay. So if I have an ammonia molecule, I do a C3. Let me call this a ABC to start with. And I do I do the first C3. So A comes here, C goes here, and B goes here. That is C3. Then I do C3-2. So A, which is here, I do not do 120, I do 240 degrees actually. So A comes here, C comes here, and B comes here. But if I do a C3-3, I go 120, 240, 360, so I come back to the same place. So the C3-3 is equal to E. So it is not a unique symmetry operation. So there's a C3 and C3-2. They both belong to the same class. That's why in the character table, you have a prefix of 2. Same way, you have 1 mirror plane, 2 mirror plane, 3 mirror planes, all having the same symmetry, same class. That's why you have in the water case, the two sigma b's are they were of not same class because they were mutual orthogonal. Here it is not. Okay, so they belong to the same class. So that's why I think in the Gilbert orthogonality theorem, when you multiply, you have to worry about the coefficients of 1, 2, and 3 for C3b, which you will see in a few minutes. So now you understand the problem of operating Cartesian coordinates by the symmetry operations for a simple molecule. It's another simple molecule such as ammonia, because it does not have rotations which involve 0, 90, 180, or 360. So is there any easy way out? I think there is an easy way out. As I said, people have worked out an easy way. You can do a very detailed matrix analysis. Okay, but I think one does not have to do this. What is this? So where am I here? Okay, so God, swiping. Just 1 second, wait. I had to close some windows. Okay, now hopefully fine. No, it's again coming back. This is another window in the. Okay, so now what you have here is a problem with this related to trigonometry. What I'm going to do in the next slide is going to introduce a simplified and easy way to do this. Okay, so I'm going to use what is called the sum of unmoved atoms plus traces from the corresponding matrices approach. Don't get scared by this, statement. All that I need to do is that I have to take the same ammonia molecule and simply break down the total Cartesian coordinates, that is the total Cartesian coordinates, into a sum of reducible representation corresponding to the unmoved atoms and traces of matrix. The trace of matrix is just very simple. Don't worry about that. I'm just explaining. Suppose I have an ammonia with the 3 atoms and you're going to only look at the number of unmoved atoms. I operate, E, none of the 4 atoms move. So my value under this would be C3. Okay. Under E will be 4. When I operate C3, this all the 3 hydrogens change their positions. Nitrogen remains where it is, so it will be 1. If I do an X is the plane, again X is normally this way and Z is the top. You please use the same convention. Even if you switch, nothing happens. But it's better to use the same convention. X is the normal X what you use in the graph, but the normal Y axis becomes Z axis and Y is out of plane. Okay, so 4 1 1. So if you do X is that plane, how many atoms change their position in the X is plane? Anybody can answer? Unmute and answer.
2.
2. Any other answer? What do you say? It's 2.
Sir, if you put a plane, then N and H will be the same. No? Plane will
Okay, N and H will be. So the plane because I showed you this diagram, nitrogen, hydrogen, hydrogen. This way is easy to see. This is a plane, right? This is a plane, right? This is one plane. This is another plane. This is a third plane. So one nitrogen, one hydrogen fall in the plane. So it will be 2. Oh, I'm sorry. I just completely got mixed up. Just 1 second. What am I doing? I'm not doing it for ammonia. I'm just doing it for C2V. Yeah. I'm doing it for C2V. I just want to do stepwise. Just a minute. I need to now come out and then erase this. Discard. Okay. I'm sorry. Okay. We are still water. Sorry. Okay. So I have only 3 atoms here. C2 is this. Both change the position and oxygen remains where it is, 1. Sigma V is XZ. So all the 3 atoms are the same plane. And here only 1 atom. Is it correct? That's correct. Okay. And then now I do a trace. Trace is nothing but is actually trace from the respective matrices. The matrix for E is represented as, just see this and forget it. I'm just only trying to justify for the people who have done a matrix algebra. This is how the E is denoted as. Okay. So the sum of the diagonal is a trace. So 1 plus 1 plus 1 is 3. Okay. So it's 3. So identity, the trace for identity matrix is always 3. And for a mirror again, for a sigma, let's say X is Z, it will be 1 0 0 0 minus 1 0 1 0 0 1, because X is X and Z are plus 1 and Y is minus 1. So the sum is 2 minus 1 is 1. Okay. The trace for a mirror plane is 1. For inversion, the matrix would be, for I, inversion will be minus 1 0 0 0 minus 1 0 0, 0, minus 1. So the sum is minus 1 plus minus 1 plus minus 1 is equal to minus 3. I think I done a mistake here. Here is there's a mistake. It should be minus 3. For inversion, the trace is minus 3. Okay, these three are done. Now comes the problem for proper and improper rotations. So the proper rotation is nothing. That's also very easy. For whether it's a proper or improper, all you need to do is that suppose I'm rotating about the z-axis. Z does not change. The x and y change. So that's what the matrix looks like, right? So it is actually cos theta. Theta is the angle by which you rotate. With C2V, it will be cos 180, cos 181. If it's ammonia, is 120 visa, it will be cos 120, 121. So instead of scaring you with all this formula, you can simply say is nothing but 2 times cos theta plus 1 for a proper rotation. I will not taught you anything about improper rotation. Suppose there is an improper rotation, it will be cos theta 0, 0, 0 cos theta 0, 0, 0 minus 1, because improper rotation is rotation followed by a reflection. Those who have done 801 would have understood this, but others also, when we go to ferrocene, I will explain this. That may be the last class, I think. Okay, so it is 2 cos theta minus 1. So do not worry if you are not studying trigonometry. I'm sure you are studying in the school. So you know that cos 0 is 1, cos 90 is 0, cos 120 is minus 0.5, cos 180 is minus 1. Okay, this is, I think, if you have a calculator, you can also ask for the calculator. Calculator will tell you what is the value. So the only things you have to remember are these numbers. Okay, you can logically remember. If you can't remember the logically, just mug it up, saying that identity is plus 3, inversion is minus 3, mirror is plus 1, rotation is 2 cos theta plus 1, and improper rotation is 2 cos theta minus 1. So if this is how you get the traces. Now we come to the example of our molecule, namely C2V. I need to fill these 4 values, right? So identity is 3, so no problem, put 3. C2 cos theta is, what is the cos theta? 180, right? Cos 180 is minus 1. Okay, I think all of you know this, I think. So it's essentially 2 times cos theta plus 1 would be 2 times minus 1 plus 1 is equal to minus 1. So the value of trace of the matrix for C2 is minus 1. For sigma V, it's very easy. It's 1. We already said it is 1. Sigma V prime is again 1. Now all that you need to do is multiply, not add, multiply the number of unmoved atoms tau by the tau trace. 3 into 3 is 9. Minus 1 into plus 1 is minus 1. 3 into 1 is 3. 1 into 1 is 1. So as you can see, this is what we did some time back by doing Cartesian coordinates. Look at the value here. 9, minus 1, 3, 1. There we put a water and put a hydrogen, and then we put a X, Y, Z for each of the atoms, and then we were adding it up. We have done the same thing in a slightly different way, same value. Now you can take this and do a reducible representation and go through the same exercise of what we did here. This one, you will essentially get the same result. Okay, so you'll get the same 2A1 and B1. So when water molecules are asked in an exam or in an assignment, it is left to you whether you want to use the Cartesian coordinates or to use the sum of, or the product of, rather. Why I keep saying sum, I don't know. The product of the tau unmoved atoms times the tau traces of the corresponding matrices. Either of the two will give the same result. You have this option of using either Cartesian coordinates. In fact, this is also Cartesian coordinates only. Only thing is, if you have a 9 by 9 matrix with the cost values, it will be too confusing. The problem has been broken down into smaller components, because whenever the atom does not move, it's 1, 1, 1. Okay, you know this. When atom moves, is either +1 or -1 for most operations other than the rotation. For rotation, you have a cos theta. So even the matrix is 9 by 9 or 12 by 12 or 15 by 15, you run into trouble. So we are breaking down into, the unmoved atoms, separate it. For moved atoms, only look at the traces. I think that's how we do this. So this is very clear. This is very easy to, very easy to do this. So you have this option only for molecules which have, C2 axis or C4 axis. But I started, introducing this idea for a different molecule, namely C3Z. Okay, so there are two ways to, to get the total reducible representation. One is use Cartesian coordinates as a basis. Other one is simplification of the above exercise, namely Cartesian coordinates, through unmoved atoms plus traces method. So, is there even a simpler method to directly obtain just vibrational modes? Because both these methods A and B shown here are essentially is going to give, because you have a 9, we have a -1, 3, 1, right? Yeah, 9 -1, 3, 1. This is the total degrees of freedom corresponds to. But I'm only now looking at the Raman spectrum or the IR spectrum. And why should I really bother about the rotational and translational degrees of freedom? Why should I go through these big numbers of 9 -1, 3, and 1? Can I have even smaller numbers? So that's essentially the thing which I'm going to teach next. Yes. So this is where you have to understand there is a much simpler method to do this. And what you actually do is what is called internal coordinates instead of the Cartesian coordinates. Cartesian coordinates are the addresses of all atoms x, y, z in terms of x, y, z. So they essentially have a 3 times x, so 3 times the coordinates. So the problem is big, but internal coordinates are normally about bonds, bond angles, and triangle angles. So let us take a molecule such as hydrogen peroxide trans. Hydrogen peroxide also has another conformer, namely the cis. Okay, this is C2V, this is C2H. Okay, we'll come to this a little later. But let us take a molecule. It's got 1, 2, okay, OH bonds, 1 OO bond, and then it's got 2 HOH angles, and it's got 1 torsional angle. Okay, torsional or a dihedral angle. That means if you assume that that's what cis trans happens. So I have this 3, and then if I take this and then rotate this bond, okay, and then bring it around this bond rather. I rotate this bond and bring this all the way down and put it here. That's because my cis. Okay, so I have my internal coordinates are nothing but bonds, bond angles, dihedral angles. This is just to explain what are the internal coordinates. Let me go back to water molecule. Okay, so I come back to water molecule. Water molecules intercoordinates are very, very simple. I think it's got 2 OH bonds and 1 OH bond angle. So why I should really worry about a 9, what was this, -3, 1, what is the number? I keep forgetting the number. What? Too much matter. Yeah, 9 -1, 3 and 1. Yeah. So why should you worry about this total Cartesian coordinates? I can only worry about the internal coordinates. So I said I have 2 bonds. That's bond A and bond B, small a, small b. I can only now do the operations about these 2 bonds. When you do identity operation, the 2 bonds remain where they are. So you can put simply 2. When I do C2, so the A becomes B and this A goes here and B comes here. So they change the positions. So that becomes 0. Sigma B is the plane of the paper or the board itself. So all the 2 bonds are remain where they are. So 2, no problem. And then when I do a sigma v prime, which is this one, b becomes a and a becomes b, so again becomes 0. So my tau OH, which will particularly only give me stretching frequency, nothing it will give more than that, is 202. Now my tau HOH angle, now this diagram, now if I operate E, it remains where it is. If I do the C2, the angle remains where it is. If I do sigma V, which is the plane, it remains where it is. I do sigma V prime, remains where it is. So essentially you get a character of 1, 1, 1, 1 and a reducible representation for HOH also. Now I am doing the same reduction of the reducible representation, reducing the reducible representation using the great orthogonality theorem. The order of the group is 4, 1 by 4, 2 plus 0 plus 2 plus 0, 4 by 4 is 1, 0, 4, 2 minus 0 plus 2, 4 by 4 is 1. So I get 1 A1 and 1 B1, which was my result earlier also. But how did I get? I took this and I reduced it, got the total number of A1s, A2s, B1s, B2s, subtracted the rotations, subtracted the translation, and finally got into the total vibrational modes. Then I looked at the symmetry and then assigned some which are stretching and which are bending. Now, without doing any of these things, by operating upon only the bonds, the internal coordinates, I directly come to the result of A1 and B1, which is your symmetric stretch, that is symmetric stretch and symmetric bending. B1, I'm getting confused. The asymmetric stretch. One is expansion, other one is contraction. Okay. Okay. So now we take the HOH as the basis. 1, 1, 1. I think it's very simple. So all in the under A1 is plus 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 plus. So 4 by 4 is 1. Here the number of plus and minus are equal under the irreducible representation. So it will be plus 2 minus 2 plus 2 minus 2 plus 2 minus 2. So all are 0 by 4. So 0, 0, 0. So essentially you get 1 A1. So you have 1 A1 bending. That's what I drew here as a bending vibration. So now if I do not give you a specific task in the hand and ask you to deduce the stretching and bending vibrational modes of water using group theoretic analysis, which one would you do? You will use the Cartesian coordinates by taking 9 coordinates and do the reducible representation, or you will use the unmoved atom plus traces method, or simply will use the internal coordinates. I think you will do internal coordinates. That's the easiest because our job is now here. If my question is that for water molecule, find out the symmetries of rotational, translational, and vibrational degrees of freedom, and also find out which of them are higher active and which of them are non-active, then you have to do the unmoved atom plus traces or the Cartesian coordinates, whichever you want. Okay. Remember, whenever you are doing this reduction of the reducible representation, you should always get an integer. Okay. You cannot get a fraction. So that is an internal check what you have. Okay. You cannot get a 1.5 or 1.66 or 1.33. Okay. Remember this. So that means your signs are somewhere reversed. Okay. Please check this. When you are doing this, that is a chi r, chi irreducible, and n times x. Okay. Sigma 1 over h. That's the orthogonality theorem. Okay. Is this clear now? I think this is, I kind of now taken water as an example, showed you 2 methods where you get a total degrees of freedom and 1 method where you get only vibrational, that too separated as the stretches and the bends. Okay. So it's time to move on now. I need to now justify why I need to introduce this, unmoved atoms plus traces of the matrices. Okay, approach. So I have already done this, but you can redo this here. So ammonia is a molecule here. You have I again drawn it in such a way that you are looking from the top. You're looking from the top. So when I do a identity operation, all 4 atoms don't move. If I do a C3, okay, all but nitrogen move, so only one. Sigma V, as somebody said sometime back, okay, one nitrogen and one hydrogen will remain unmoved. So the tau atoms that do not move is 4, 1, 2 under E, C3 and sigma V. The tau under the traces, you have to again go to this formula. Under E is 3, under C axis C3 here is 2 cos theta plus 1, and sigma okay, is equal to 1. I and S we don't have in this molecule, don't worry about it. So it's easy. So you can put under in a E trace, you put 3 under 2 cos theta plus 1. You know cos 120 is, how much cos 120 is? Minus 0.5. So once again, let me write here. Cos 0 is, cos 90 is, cos 180 is. So it's minus 0.5. So minus 0.5 into 2 is minus 1 plus 1. 2 cos theta is equal to 0. So you get a value of 0 here. And sigma I already told 1. So again, what you need to do is you have to multiply 4 into 3, 12, 1 into 0, 0, 2 into 1, 2. You can also multiply the coefficients, but I don't want to confuse you here. Okay? You can also, instead of writing 12, 0, 2, you can write 12 into 0 into 12, 0, and 6, but it's not necessary. So essentially, I used the tau unmoved and tau traces and got these values of 12, 0, 2. Okay. Now, the next slide, I have drawn the character table once again. This is the character table, what you see here. Okay. So, 1202 I have taken from here and then written here in the bottom, tau red. Okay, this is total. Okay, like Cartesian coordinates. I didn't use Cartesian coordinates, but I use this unmoved atom plus traces formula. I have 1202. So I multiply 12 by 1, 12 by 1 by 1. So that's what is this. 0, 1 into 2. It's not the same order. 0, 1 into 2. 2, 1, 3. 2, 1, 3. So this is 12, 0, 6. So 18 by 6 is 3. So 3 times A1 occurs. Now I'll have to operate upon operate upon this row. So 12 into 1 into 1, that is this. 2 into 0 into 1, 2 into 0 into 1, and 3 into minus 1 into plus 2. 3 into minus 1 into plus 2. So this is 12 plus 0 minus 6. 12 minus 6, 6 by 6 is 1. So 1 time A2 occurs. So just before I proceed, let me just tell you that E is a two-dimensional Mulliken symbol. Under identity, it has to be 2. I told you in the last class. If you've forgotten, I just want to remind you that if it suppose there were a T there, three-dimensional one, under E it will be 3. Okay, so remember that. So 12 into 2, 0 into minus 1, 2 into 0. So this becomes 0, this becomes 0, this becomes 24. 24 by 6 is 4. Okay, 4 times E occurs. So total, this is a reducible representation is this. The total irreducible representation, okay, for all degrees of freedom is that 3 times A1, 3 times, 1 time. This is a 2-dimensional one, so it's actually 4 into 2. It actually 8 degrees of freedom. 8 plus 1, 9 plus 3, 12 degrees of freedom. Is this point clear? I think all of you. How do we how did we obtain the 12 degrees of freedom for, because this is water has got 3 atoms, you had 9 modes. Ammonia has got 4 atoms, you have 12 modes, of which 4 of them are non-degenerate and 4 of them are degenerate, doubly degenerate. So 4 into 2, 8 plus 4, 12 modes. Okay. Now we can go back and do the same exercise what we did for water. This is the total degrees of freedom. And if the character table, you see that translation corresponds to 1 A1 and 1 E. E is actually 2. Okay. If you want to see the character table, I'll quickly take you back. Where is this C3 character table? Where is this? See, C3 character table. This is non-degenerate. This is degenerate. This is non-degenerate, and this is degenerate. Okay, this is A1. This is E. This is A2. This is E. So essentially, you have to subtract 1 A1, 1 A2, and 2 E's. That's what you have done here. So you have subtracted, 1 A1, 1 E for translation, 1 A2, and 1 E for this. So finally, you are left with 2 A1s and 2 E vibrations. Okay. There are 4 vibrational modes. For ammonia. Okay. What are they? That's where you get stuck when you do this method. Okay. So what I have not done here in the slide, what I'm going to do, I think using an empty slide, is the internal coordinates of the basis for ammonia. I will not go through this. I will come back to this later. Okay, so we have some clean slate. Now we will start from using so I'm using internal coordinates because I know from the full Cartesian coordinate analysis that I have 2 A1 vibrations and I have 2 E vibrations. Okay, 1 E vibration, 1, right? 2 E vibrations, yeah. So vibrations, but I do not know how much of them are in this stretching and how much of them are vibration, the bending. So one way I can overcome this problem is assign these bonds as ABC and angles as 1, 2, 3. Okay, these are my internal coordinates. ABCs and small Roman 1, 2, 3 are my internal coordinates. Now I just draw the character table once again. I have a E, and I have 2 times C3, I have 3 times sigma V. I'm going to do tau NH, which will essentially give me the stretching vibrations. And I'll do a tau H N H, which will give me the bending vibrations. Are out of plane. Okay, now I take now E and operate upon this molecule and then see how many bonds are changed. How many bonds are changed? None are changed. A, B, C, they stay put. Okay, so you have a value of 3 here. If I do this for the C3, that is, this is perpendicular to the plane of the board of the paper. So A goes to B, B goes to C, and C goes to A. All the 3 bonds have moved. Value is 0. When I do sigma V, it doesn't matter which sigma V, all 3 are the same class. You see that one bond remains where it is, the other 2 bonds move. Okay, so, this bond, suppose this is my mirror, the A bond remains where it is, the B bond and C bond change its position. So the value under this is 1. I can do the same thing for the angle. I once again draw the molecule for simplicity's sake. I have only these 3 angles. I call this 1, 2, and 3. If I do E, all 3 angles remain where they are. And I do a C3, again all 3 angles move around. 3 becomes 1, 1 becomes 2, 2 becomes 3, 0. And I do the mirror again. 1. If I do the mirror, 1 angle. If I do this mirror, this angle remains where it is, but this goes here and this goes here. So again get this. So my tau values for stretching and bending have been factorized or been separated out as stretching and vibration and bending. And if I quickly go to the character table, or rather I write the character table here. Yeah. So A1 is 111. A2 is 1, 1 minus 1. Remember that A is always symmetric with respect to the C2 axis, principal axis. So it cannot, this cannot be minus 1. So this has to be minus 1. And E is, as I said, 2 has to be here. This is 0. I'm sorry, not 0. It's minus 1. And this is 0. Okay, that's the value. I don't have space in this slide, but I can just kind of make use of this much of space and then do a tau number of A1. I'm doing only for the NH stretching variations is equal to order of the group is 6, 3 plus 2 plus 1 is 1 by 6. That doesn't change. 1 into 3 into 1, that is 3. 2 into 0 into 1, 0. 3 into 1 into 1, 3. So 3 plus 3 is equal to 6 by 6 is equal to 1 A1. So N A2, 1 by 6. So I take the E multiplied by tau NH with this row. So it will be 1 into 3 into 1. So 3. 2 into 0 into 1. So am I right? 2 into 0 into 1. 2. 3 into 1 into something is going wrong. Wait. 1 times 3 times 1. 1 times 3 times 1. 2 times 0. This is 0. And 3 times minus 1 is minus 3. 3 minus 3 is 0. So 0 A2. Number of E is equal to 1 by 6 into 2 into 3, 6 plus 0 plus 0 is equal to 1. So it's easy now that you already know that 1 A1 and 1 E vibration are the NH stretching vibrations. You can do the same exercise using this. It's not going to be any different because the values are 330011. So again you will get H N H, okay, tau as A1 and E. So if you go back to the previous slide, you got two A1s and two E, of which one A1 and one E is stretching vibrations, and one A1 and one E is bending vibration. So this is the advantage of using internal coordinates as against the Cartesian coordinates. Cartesian coordinates give a lot of information, but you need to separate them out. Vibrations, rotations, and translations, and within the vibrations you have to see which is symmetric and which is asymmetric, or which is bending and which is stretching. So you have all these problems sorted out when you do this as the internal coordinates as a basic. So although I have taught you in the last couple of classes, in this class, how group theoretically you can approach to find out the degrees of freedom and assign the spectral frequencies. The easiest way for IR spectroscopy is just to use. In fact, apart from this stretching and bending, also the rocking, out of plane vibrations like hydrogen peroxide trance I showed you. I'm not going to do it today. Okay, I'm going to do something else in the next 10 minutes. What I have. So I will also be talking about not just bonds as a basis or angles as a basis. I will also talk about dihedral angles as a basis. This is for stretching vibrations. This is for bending vibrations. This is for out of plane vibrations. I just show you what it is for hydrogen peroxide. So these two can come up and these two can go down. Okay, this kind of two atoms move up and two atoms move down. Okay, this is not a bending. It's not about an angle, but it's about a dihedral angle. Okay, so dihedral angles are over 4 atoms. So the internal coordinates come very handy to do this. So what I want you to do, you people to do at home, is to go back and look at some others. So I showed you. I only worked with the two molecules today. One is C2V, water, and one molecule is C3V, which is ammonia. I want you to work on another example of a C2V. Which is hydrogen peroxide. So it has a C2 axis running here. Sigma V is the plane of the molecule itself. The other sigma V is here. These are the sigma V. Okay. So these are the point group remains the same. Water versus H2O2. Both are C2V. The 3 atoms, 4 atoms. 9 degrees of freedom. 12 degrees of freedom. Vibrations 3n minus 6. 3n minus 6 is 12 minus 6 is 6 vibrations. So the number of atoms increases for the same point group, the vibrational mode increases. So if I were to start all over again by assigning 3 Cartesian coordinates for each of the 4 atoms, I'll have a 12 tau red Cartesian, under E I'll have 12. Okay. You can do this actually. You can do this for practice. Okay, you can find out what are these. That is part A. Part B is switch over to internal coordinates. Part A is Cartesian coordinates. Part B is switch over to internal coordinates. So you can do simply tau HO and do a tau OO and do a tau HOO. That's this angle and this angle. Okay? And then there's a tau HOOH. These two will give me information about, that's what I said, about the stretching vibrations. And this will give me about the bending vibrations. This will give me information about out of plane vibrations. Even within the stretching, I can find out what is the symmetry of the OH stretch and what is the symmetry of OO stretch. Because you will have 4 reducible representations. Okay. All of you, can you do is a homework for a, for a very small weightage of your total marks. Please do it with a pen and paper, okay, on a piece of paper. Just and then all you need is that you have to write the character table for C2V, which I think now you should remember by your head. And by 1 1 1 1 1 minus 1 minus 1 1 minus 1 1 1 1 minus 1 minus 1 1. Okay, so that's the C2V character table. Then now you can do the OH. You can take a hydrogen peroxide, operate only on these 2 bonds. You get the tau HO, and operate only on this bond, and you'll get the tau OO. So you'll get some number. Okay, A B C D under E C2 sigma V and sigma V prime. Same way you will get a prime, B prime, C prime, D prime. You reduce A B C D, you get only OH stretching frequency. You reduce the A prime, B prime, C prime, D prime, you get the OO stretching frequency. I think this is a fun to do this. I think will you try this in at home and send me as a assignment by 8 in the evening today? By 8. I think you can use
so you're saying today 8, right?
Yeah.
So we have classes, sir.
Yeah, we have class.
But this takes about 5 minutes. Okay. Okay. Do it by tomorrow morning, 10 o'clock. Okay. Let us all. Okay.
Okay, sir. Thank you, sir.
So see the YouTube channel what I have is also the same username. Okay. CH521IC@gmail.com. Okay. Please mail it there.
Sir, can we just upload it as an assignment on MS Teams?
I can do that. Okay. But I already given it. I think one of you can do this actually. Ashi or Arsha or Gargi can just deduce the all the degrees of freedom for hydrogen peroxide trans. Cis is not trans. It's trans I want to do in the class. Cis I want to do. Trans goes to a different point group. Cis is C2V. Trans is C2H. It has a I component I want to do in the class. That is I think tomorrow's tutorial I will do the C2H. So what I'm saying is that you do hydrogen peroxide cis, all the degrees of freedom, rotational, vibrational, and translational, because you don't have a cos 120 problem here. It's all 180 degrees and 0. It's very easy to do Cartesian coordinates, and you can even if you don't know how to do Cartesian coordinates, I think I've taught you a simpler method today. How to use the number of unmoved atoms plus the traces. Traces times the unmoved atoms also gives you the same Cartesian coordinates tau. You can operate upon, get the total symmetries of all the 3 degrees of freedom, 3 types of degrees of freedom. You can subtract rotation and vibrations and get only the rotation translation, only get the vibrations. And then, as I said, you can do only bonds, angles, and dihedral angles. The 3 of them as separate tau reds, tau reduced representations, and operate upon. I just want you to do this. It's just me doing it. I think you won't get a feel for what I'm telling. There are also solved hydrogen peroxide in the internet. You can also see there are some videos, there are some PDF files. You can see it once, but close it and close the video, close the screen, and then take a paper and then a pen and then do it yourself. Write down the character table by looking at it. I don't want you to remember character table. It's not necessary. Once you write the character table, tau reduce, you have to reduce it. Okay. and do it yourself. If you make a mistake, there's an internal check. I told you, if you make a mistake, your division of the it summed by the order of the group, it should give you an integer, 1 or 2 or 3 or 4, whatever it is. It can't be a fraction. So that's an internal check. So you can go back and check yourself. Okay, please do this. Okay. I'll set it up as a an assignment. Do it by tomorrow. I think tomorrow sometime. I think this is very important. Okay. Actually, what I want to do was the next molecule I wanted to do is the 438 folks would know that I talked about this molecule. I talked about the main group chemistry in a beautiful example of a BSAPR model, right? Seesaw molecule, right? SF4. And SF4 should be TBP, of course, because of the the lone pair. I think these two bonds get slightly bent and it goes to a seesaw type. So essentially, you have this C2 axis sigma V. Okay, and these two are out of plane. Okay, and this is the one plane sigma V, and the other one is these 3 atoms. Okay, so SF4 is another beautiful example of C2V molecule. Now, what has happened here? You have 5 atoms. So water C2V 3 atoms, H2O2 4 atoms, and SF4 5 atoms. All are C2V. Okay, 9 degrees of freedom, 12 degrees of freedom, 15 degrees of freedom. 3 vibrations, 6 vibrations, 9 vibrations. So I was planning to do in this class only this SF4, but I think we are reaching the time limit. I think there are a few minutes, but I don't want to start this. But on the other hand, I want to use this next 10, 12 minutes. It's available for taking any questions online. Please go ahead. Wherever you have trouble understanding, please unmute your mic. Can they unmute their mic, Harsh? I think they can, right? All of them? Yeah, they
Yes,
can unmute.
Professor,
Yeah.
they can.
And those who want to ask question only, please unmute and please ask. Yeah.
Yes.
Yeah, please go ahead. Yeah, I need some feedback from you people. I think see, I may understand everything what I'm writing, but if you don't understand, there's no point in going through all this exercise 2 times or 3 times. So wherever there's a doubt, you have to tell me. That helps me to prepare for the tomorrow's plan tutorial. No one has any doubts?
Yes, sir, I have a doubt.
So,
Yeah, please.
So, sir, how we know that suppose A1 is in C2V molecule, I think A2 is for Rx, so rotational for x-axis. So how we know that?
Okay, see, I'm just going back. As I told you in the last class as well as today, a character table has got different regions. Okay, these are the regions. You can see this, right? So this, what I'm just, can I get the highlighter out 1 second? Highlighted. Okay, now what you have here is a Mulliken symbol. That's the leftmost part of the character table. Okay, and then what you have here is the heart of the character table. What I'm just circling now. These are the characters, right? These are the characters 1, 1, 1, 1, 1, minus 1, 2, minus 1, 0. And these are easily derivable. I mean, like when I did my master's, we had a full group theory course, which we unfortunately do not have nowadays. Okay, for the masters, we can derive these, the functions and the quadratic functions. But somebody has done and kept it for you. Okay, so you don't have to memorize this. All that you know is that in the region, function region, whenever there's an occurrence of S, X, Y, and Z, they correspond to T, translation. Okay, some books call this a TZ, TX, and TY. Some books don't. But if there's no prefix, this is translation. So it is already kind of told you beforehand that the representation okay, with the A1 and E correspond to a non-degenerate and degenerate translational modes. Same way, this RZ and this RX and RY again tell you that the rotational modes, there are three rotational modes, right? There are three rotational degrees of freedom. They correspond to, one corresponds to a non-degenerate A2 symmetry, other corresponds to E. So you have to look at the character table. That's why I'm saying, even in an exam, if we are going to ask you a question to reduce all of this, we will give you the character table. Okay? The deduction of character table itself is the part one of the group theory. Okay? Part one of group theory is understanding the mathematical model of the group theory, understanding the regions, how to derive these numbers. Each of these numbers on this table, each and every part of this, this character table can be derived. I thought Professor Anil that did it. Did he or did he not? Hello.
So in the group theory course, we are only starting with great orthogonality theorem.
Okay,
now.
so probably the chemists have probably assumed that this is too much of mathematics. Okay, it's just see, if you are good in algebra and trigonometry, it's easy to do it. If you are not, I think I completely agree with Anindya. You start from great orthogonality theorem, but have some feeling for this identity operation, C2 operation, C3 operation, sigma v prime. Without a feel for these symmetries, you cannot directly jump to orthogonality theorem. So you need to know these regions, and these are quadratic functions. What I'm just crossing out now, which are point of interest only for Raman. Raman is a two-dimensional property actually. It's a polarized, right? The polarization leads to Raman. So it is just a univector quantity cannot explain a Raman mode. So you need this. So this region has information about rotational, translational, and IR. This has got information about Raman. Did I answer your question?
So, yes, sir. Yes, sir. I got. Actually, I did not understand how to obtain RZ for A2.
No. I see, if all of you are interested in knowing this, December month, Christmas month, we will have a few tutorials if you want, only for the interested students. How to derive at least water character table. It's very easy to derive. Okay. I can derive the entire table and show you how, where to put Z, where to put X and Y, where to put R, Z, R, X, Y. Okay. It's not very difficult. Okay. Same way, the p orbitals and d orbitals, how do they get there? The symmetry elements, right? You use A1, A2, G, AG, AU, E, and T. I taught you the first year BS students, the T2G and the EG, right? Triple EG. These all come from group theory. Okay. So these all come from group theory. I can do this only for the interested individuals. I don't want, because we have large number of PhD students in the class who come from physics, chemistry, biology background now, with no mathematics. So let's have some concern for them and not get into too much of mathematics. Okay, any other questions? But I think the little bit I taught you about this, where is that? I don't know, where is that? Yeah, this one. Okay, this I think you have to have some, you don't have much option other than to, remember this 2 cos theta plus 1 for, rotation. Because the other things are very easy to remember, okay? Those matrices, please remember, 1, 1, 1. That's how it looks like for E. C2 is -1, -1, 1. If you're rotating about Z axis. And if X is that plane is a mirror, this is how it looks like for a mirror. This is mirror. This is C2. This is E, capital E rather. -1, -1, -1. I. So the sum of this diagonal elements is 3, -3, plus 1. Here -1. For C2 it's easy. Okay, because 180 degrees. For 120 it is, so that's why I replace this -1 by cos theta. That much math all of you can understand or not? So when you put theta is equal to 180, it becomes anyway -1. If it is cos 0, it will be something different. If it's cos 120, it will be something different. Okay. Remember that. Okay, so I think then it's time to say goodbye. Now I will send these slides. Okay, I have not sent you any slides about group theory. The slides what I taught today is essentially a bit more organized in a form of the Monday's lecture, which is more of a free handwriting. Here I use some downloaded tables and other things. So go through this. We need to fix a time for tomorrow's tutorial. Okay, please. I think you converge within yourselves on the WhatsApp group and tell me what is the time. Because I do not have as of now any meetings or any assignments to be done tomorrow. Although I normally avoid the time between 12:30 to 2, okay, to 2:30, okay, okay, and then please come back. I can do a few more examples of this one only, and introduce a few more concepts in IR spectroscopy. I initially thought NMR I will do it, but I think I'm just giving up on NMR instead of teaching too many things. NMR has been taught by Kulkarni. I will only spend the next 2 classes of the next week before I pass on the baton to Professor Agri. IR spectroscopy, because the idea is not to teach water and ammonia. I have to teach metal complexes, palladium complex, platinum complex, metal carbonates, how I use group theory to get my vibration frequencies. Okay, that's what I'm going to do in the next 2 classes. So this is the foundation for the complexes which I will be dealing with in the classes next week. So let us have a tutorial tomorrow. Saturday is also okay for me, but I think it's a puja. I think many people have a very busy schedule at home. So all of you are at home. If you are in the hospital, it's a different issue. So tomorrow find some time and come back to me. Take care. Bye bye.
Thank you, sir.
Yeah. So if you are recorded, please download it, Ash. I think I probably also recorded it. Let me check it.
Yeah, I think you can turn off the recording. It's still
Yeah.
on, I believe.
I'm just doing it.